coronal mass ejections. The field changes very rapidly in time and quite significantly in space from across the disk to the smallest size we can measure. Here is an animation where we start with a full disk image from SOHO, zoom in on a patch of the sun, and then compare the SOHO view with a higher resolution image from the TRACE satellite. We see far more detail in both time and space with the high-res version. Based on this type of animation, AIA was designed to return high-res versions of the entire disk, allowing us to zoom in on any part we want without having to sacrifice the ability to look at all parts of the sun. The third instrument, EVE, measures the extreme ultraviolet emissions of the sun, which create the ionosphere and are involved in many space weather applications. Here is an example of what those emissions look like during the decline of solar cycle 23. The C instrument on time measured these since 2002, but only every 90 minutes. We now know that we should measure them much more quickly at a pace that matches more what we want to understand for these important emissions. Our data will be made available through our website at sdo.gsfc.nasa.gov, which we encourage you to visit. And now, thank you. Liz Citrin will tell us about our preparations for launch.
Thank you, Dean. After completing more than 6 months of environmental testing and performance verification at Goddard, SDO was packed up and shipped to the launch site processing facility by truck. We arrived in the rain. SDO is processing at Astrotech, a commercial processing facility about 10 miles from Kennedy Space Center. After arrival and waiting out the storm, SDO's moved into a clean room at Astrotech for final testing. You see, we need to make sure that the observatory survived the trip down to Florida without any problems. To do this, we repeat what we call our comprehensive performance test. It's a 7-day test where all elements and components of SDO are verified to be operating correctly. This next photo shows SDO in its test configuration. We're horizontal so that we can shine light into the instrument telescopes. Another step in our testing is testing our deployment mechanisms. Here you see our high-gain antennas being deployed. We also deploy the solar arrays, and we pop the doors on the instrument telescopes. After we've confirmed that everything is okay with SDO, we fuel. This is a 6-day hazardous operation performed by trained personnel in scape suits, protective suits with their own air supplies. And at this point, we're ready to start our integrated flow with the rocket. We're launching on an Atlas V rocket. This photo shows the Atlas rocket already stacked at the VIF, the Vertical Integration Facility. The photo shows the Centaur second stage being lifted onto the Atlas booster. And that's where we are right now in the flow. The next step for SDO is encapsulation. This is occurring right now at Astrotech. Then, protected by the fairing, SDO will be transported to the VIF and lifted on top of the Atlas stack and mated to the rocket. After a couple of weeks of testing and final closeout activities, we launch. SDO's launch date is February 9th at 10:26 in the morning. If we can't launch on that day for weather or some other reason, we'll try the next day. SDO can launch pretty much any day of the year. Let's watch this animation of launch in early orbit. Here's SDO in the fairing on the rocket. The rocket's on the pad. Ignition, liftoff. The Atlas first stage takes us through the boost phase and then falls away. The second stage Centaur burn starts right before fairing jettison, about 4 minutes into flight. We stay on the rocket for almost 2 hours. Then the Centaur points us in the right direction, burns again, and we separate from the rocket. This is a critical time for SDO. We must deploy our solar rays and point to the sun quickly to get power to our spacecraft. Then we breathe a sigh of relief. We have a 2-month commissioning period where we methodically test all of the spacecraft components and our instruments. Also at this time, SDO is using its propulsion system to move into our geosync orbit. Finally, SDO is fully checked out. We're on station, we're pointed at the sun, and we're sending back amazing data and images of the sun at the rate of 1.5 terabytes per day. Unbelievable. And we're going to do this for 5 years or more. We can't wait for this data to start flowing. Thank you.
Okay, well, thank you all. And we're going to open it up for questions, but I would like to make one statement. We talk about diversity here at NASA, and we certainly take that very seriously. And I've had the pleasure to work with some incredible science teams and project teams at the Science Mission Directorate. And the SDO team is extremely diverse and probably one of the more diverse teams for NASA project. Of course, you've met Lika and Liz. I also want to acknowledge in the audience the program executive at SDO, Dana Brewer, sitting here at NASA headquarters. And certainly as we move forward to launch, you will get to hear more from this incredible team. And I am looking forward to the diversity and also the incredible science with this mission. So with that, we're going to open up for questions on our phone lines, and we will see where we need to go here. I have on my screen here from one of the space.coms, and I believe this is for Dick. For you, after SDO, what's up next in the heliophysics portfolio?
Well, that's a good question for me. Thank you for asking me. After SDO, we have a second mission for the LWS program called Radiation Belt Storm Probes, RBSP. And that's a back to the Van Allen belts mission. We're going to try and resolve some of the ambiguities of space and time with a 2-spacecraft mission that will be going through the magnetosphere at the same time SDO is observing. So our hope is to see cause and effect. Now beyond that, that's to be launched in 2012. Beyond that, in 2014, we're going to have a physics investigation of the day side of the Earth, where the magnetic field of the Earth and the magnetic field of the Sun mix. And there's a process there that we think may be a universal process throughout the universe that we may be able to test there because that's the laboratory we have. And this is called reconnection. And reconnection is where two fields touch and you turn magnetic energy into heat and light all of a sudden. And so this is what we're interested in and up for after this mission. And heliophysics, as Dwayne says, science never sleeps. This is a physics study which has not only knowledge at the output, but also utility. And I'd like to remind the audience that heliophysics is the science of space weather.
And I just want to take us beyond 2014, that we have some other missions actually in planning stages right now. They are not quite in development stage like Radiation Belt Storm Probe or MMS. We have a NASA, all NASA mission called Solar Probe Plus. And this is a mission that's actually going to visit the sun. It will be in the corona, the eclipse pictures that we see, it will be in that vicinity to actually really sample the material there instead of doing remote sensing observation. We also have a notional mission right now, which is in partnership with European Space Agency called Solar Orbiter, which will be out of the ecliptic and about 0.25 AU, really giving us a different perspective of the sun.
Okay, I have a couple of more space.com questions on my screen, but we're going to go to the phone lines now. And first up will be Rachel Cortland from New Scientist. Rachel?
Yeah, hi. I'm sorry if you're going to be repeating yourself, but the phone line cut out for a while. I was wondering if you could say what the overall cost of the mission is, and also if you could explain in more detail what SDO will be looking at and its capabilities compared to previous orbiters, how it's going to improve things.
Okay, Dick, you want to start that, and then maybe Dean and others can chime in with the science.
Well, I can take a cut at your costs. The SDO mission had a final confirmed price of, I think, about $808 million. We've had a slight delay, and well, it's a considerable delay, and we put money into maintaining that. So I think that the cost to complete plus the science investigation is going to be around $848 million. Now, Dean really needs to comment about the comparison, because the comparison of